Hello, in this lecture, we'll learn about elementary Fuchsian groups. Elementary Fuchsian groups are a particular type of a Fuchsian group. So a Fuchsian group is said to be elementary if it has finite orbit in the hyperbolic plane union its hyperbolic boundary. So let us begin. Okay, so let us begin with the definition of elementary Fuchsian group. So here I have defined this elementary Fuchsian group for the group PSL2R. So the same you can define for PSU11, which acts on this PSU11. It's the group which acts on the unit disk model of hyperbolic plane by isometry, and also it acts by the orientation preserving isometries on this unit disk model. So I'll be doing here this elementary Fuchsian group thing for the group PSL2R. The same you can do it for the PSU11, because both the groups PSU11 and PSL2R, so they are isomorphic to each other. So a Fuchsian group gamma is called elementary Fuchsian group. So if there exists a finite orbit of gamma in the upper half plane union the boundary of this upper half plane. So what is the boundary of this upper half plane? It is R union infinity. Okay, note that. So if I take an element T from gamma, so T, it acts on this upper half plane by Mobius transformation, and that transformation you can extend it to R union infinity. Yeah, so let me repeat the definition of this elementary Fuchsian group. So a Fuchsian group is elementary. So if there exists a finite orbit of gamma in this H2 union del H2. Yeah, so that is, so there exists a point Z either in the upper half plane or in R union infinity, such that this orbit, which is gamma dot Z, so this is a finite set. So what is the definition of this orbit? So this is this set GZ, where this G belongs to your gamma. Okay, so now let us come to example. So let us take the cyclic subgroup generated by this hyperbolic isometry Z goes to lambda Z. So at this lambda, let us take it to be greater than 1. So why this is an elementary Fuchsian group? So this hyperbolic isometry, if I take this hyperbolic isometry f lambda Z equals to lambda Z, so this, so what is, so fixed point of this f lambda, so this is 0 and infinity. So if I apply f lambda on 0, so this is equal to 0. Now if I take any element from this group, so any element will be of the form Z goes to lambda to the power n Z. So that element will fix 0. So therefore, so this will be an elementary Fuchsian group. So this will be an elementary Fuchsian group. So Z goes to the cyclic subgroup of PSL2R generated by the Z goes to lambda Z will be an elementary Fuchsian group. And the next example is again in the same way. So if I take this parabolic isometry, Z goes to Z plus A, So this will fix the point infinity. And if I take any element of this group, it will be of the form z goes to z plus na, and again that will fix infinity. So the orbit of infinity, it is just the singleton set infinity. So therefore, so this again, it is an element-free Fuchsian group. And again, if I take this F to be an elliptic element, so F will fix a point in the upper half plane. So all the elements of this group, it will fix that point. So because I have taken the cyclic group, so all the elements of this group will fix that point. So the orbit of that point will be naturally a singleton set. So this group is again an elementary Fuchsian group. Now let us come to this theorem. So let us take a subgroup of this PSL to R, and let us assume that so this gamma, it contains only elliptic elements apart from this identity. So all the elements of gamma apart from identity are elliptic elements. So then we'll prove that, so then all elements of gamma have same fixed point. So it will, all the elements will fix a same point. So hence, so this gamma will be a elementary group. So the orbit of that point, that fixed point, will be a singleton set. So therefore, this gamma will be a elementary. Okay. All right. Okay. So in fact, here, so we'll take the unit disk model of the hyperbolic plane. So we can assume this gamma to be a subgroup of PSU11. Yeah. So either you can take this subgroup to be, this gamma to be a subgroup of PSL to R, and PSL to R, it is isomorphic to PSU11. So I can take this gamma to be a subgroup of PSU11. Yeah. And PSU11, it is orientation preserving isometries of this unit disk model of hyperbolic plane. So therefore, gamma is subgroup of that thing. Okay, so now let us take an element F belongs to gamma. And F is not equal to identity. And by the assumption, so F is an elliptic element. So F will fix some point of this unit disk. So F will fix some point of the unit disk. So without loss of generality, we can assume the fixed point of F to be 0. So we are working with this unit disk model. So F will fix some point Z0, let us assume. So Z0, it belongs to this unit disk. And I can have an isometry of this unit disk, which will take this Z0 to your origin. Suppose G is that thing. And now if I take GF G inverse, so that isometry, so it will fix the point 0 or the origin. So therefore, without loss of generality, I'll just assume this F, it fixes 0. Okay. So F fixes 0 and Fz. So Fz will be of this form. So because f0 is 0, so this will imply that this b is equal to 0. So therefore, so the matrix for this f, the corresponding matrix, so this will be of this form. It will be this diagonal matrix. Okay, so therefore, so that's why I have written it here. So fx is 0, so f is of this form. So f, the matrix corresponding to f, I'll write like this. So matrix for f is equal to, the first row is u0 and 0 u1. Now let us take an isometry of this unit disk such that this G, it belongs to your gamma. And let us take G to be not equal to identity. So the matrix of this G, it is AC, C bar, A bar. So G of Z, it will be like this. For some complex numbers A and C, where mod of A square minus mod of C square is equal to your 1. So the corresponding matrix will be AC, C bar, A bar. Okay, so now if we compute the trace of this commutator, so what is this square bracket? So F inverse G inverse. So this again, it will be a Mobius transformation. Take the matrix of that thing and take the trace of that matrix. So trace of the commutator, you can compute it, and it will turn out to be equal to your 2 plus 4 times mod C square times imaginary part of U square. So this computation you can do. And now what you have assumed that, so this gamma, it contains only elliptic elements apart from identity. So this commutator, so this f and g, it belongs to your gamma. So the commutator, so this will also, it will belong to your gamma. So this is either identity or an elliptic element. So that's why, so trace of this matrix, it cannot be greater than 2. So if it is greater than 2, it will be a hyperbolic element. So it cannot be greater than 2. So if it is identity, so the trace will be equal to 2. And if it is an elliptic element, the trace will be less than 2. So the trace of this matrix, so this is less than equals to 2. Now you come to this equation again. Here, so the left hand side is less than equals to 2. So this will imply that, this part, so this will be less than equals to 0, and that will imply, so we have a square here. So that will imply that either C is equal to 0 or the imaginary part of U is equal to 0. So if the imaginary part of U is equal to 0, that means that U is equal to U bar. And also what we have, So u bar is equal to your 1. So from that thing, so what we'll get? So the matrix corresponding to this F, so this will be nothing but your this identity matrix. Yeah, so this will be nothing but the identity matrix. Okay. So this is a contradiction because yeah, so this identity matrix will get in the PSU11. So this is a contradiction. This is a symbol for contradiction. So this is a contradiction. So therefore, so this imaginary part of u is not equal to 0. So that will imply that so the C is equal to 0. Now if C is equal to 0, so G we have taken to be this thing. So G we have taken to be this. So therefore, so this G matrix for G will be this thing. C is equal to 0. And therefore, so so G of Z is AZ by A bar. So therefore, G of 0 is equal to 0. So the fixed point of G is just the singleton set 0. So we have taken G to be an arbitrary element of this gamma, and we have proved that G of 0 is equal to 0. Okay, so we have proved this theorem that all the elements of gamma have same fixed point, and hence this gamma, so this will be elementary. So now in additional, suppose this gamma, it is a Fouchian group, means it is discrete and contains only elliptic elements. So then, so this gamma has to be cyclic. So non-identity element Fouchian group is cyclic. So if I take a gamma which is Fouchian and contains non-identity elliptic element, so all the elliptic element will fix a single point. So fixed points of all the isometries are same. So therefore, so all the elements, yeah, so in fact, so they will commute with each other. And by our previous class, so that group has to be cyclic. Yeah, so we have this corollary. Now the next theorem, it states the following. So this is also a very important theorem. So this classifies all the elementary Fouchian groups. So any elementary Fouchian group gamma is either cyclic or is conjugate in PSL2R to a group generated by this hyperbolic isometry Z goes to lambda Z, where this lambda is greater than 1, and this map Z goes to -1 by Z. So you take the group generated by Z goes to lambda Z and Z goes to -1 by Z. So this will be a Fouchian group. So any elementary Fouchian group, if it is not cyclic, will be conjugate to this kind of group generated by these two elements. Okay, so the proof is done by case. So what is the case 1? So suppose there exists an element Z naught in the space, this upper half plane union the boundary, such that the orbit of Z naught is just a singleton point Z naught. So again, Now two cases will arise. Suppose z naught it belongs to this upper half plane. So this means that gamma dot z naught is this singleton set z naught. So this again this means that so every non-identity element of gamma it fixes the point z naught. So it means that so all the non-identity elements of gamma are elliptic elements. So therefore, by our previous result, so this gamma, so this will be a cyclic group, and we are done. And now, if I assume, so this Z naught, it belongs to this boundary, and also you have assumed this orbit is a singleton set. So now it may happen that, so this gamma may contain parabolic or hyperbolic elements. So we'll rule out some cases. So before that, let us prove this observation. So what is the observation? So parabolic and hyperbolic elements in a Fouchian group cannot have a common fixed point. Yeah. So this is a very important observation. Okay. So let us first prove this observation. So suppose we have two elements. One is parabolic, another is hyperbolic, which fixes a same point in the boundary. And without loss of generality, so that point, I'll take it to be infinity. So let G be a hyperbolic element and F be a parabolic element in gamma such that G fixes infinity and F fixes infinity. And also note that by our assumption, so this orbit is just a singleton point, infinity. So again, without loss of generality, I can take this hyperbolic element which fixes infinity of the form z goes to lambda z for some lambda greater than 1, and the parabolic isometry to be z goes to z plus a. Okay. So gz is equal to lambda z and fz is equal to z plus a. And now for each n, let us take this conjugate. So g to the power minus n f g and z. So that if we compute, so this will turn out to be equal to z plus a by lambda to the power n. And this tends to z as n tends to infinity. So this proves that so this sequence of isometries it converges to identity pointwise. And all these points of the sequence, so this belongs to your gamma. So it belongs to your gamma. So gamma is discrete, and these are all these elements are so g to the power minus n f g to the power n. So those are distinct elements. So that cannot be an eventually constant sequence. So this will contradict that. So this gamma is discrete. So therefore, so we have this observation. So parabolic and hyperbolic elements in a Fouchian group cannot have a common fixed point. Okay. So therefore, what we have, so elements of gamma are either parabolic or hyperbolic. Okay. Now suppose all the elements of gamma are hyperbolic. So let us take two elements. So Fg belongs to your gamma. And again, here we have assumed that so gamma dot infinity is equal to your, sorry. So this orbit is equal to the singleton set. So without loss of generality, I can assume this z naught to be infinity. Yeah, so again I can have some isometry which will take this z naught to your infinity. Suppose f of z naught is equal to your infinity. So then you can construct a group gamma 1 which will be conjugate to this uh, gamma with the help of the map f. So suppose all the elements of gamma are hyperbolic and gamma dot infinity is infinity. And let us take two elements, fg belongs to gamma, and let us assume this. Yeah, so again, without loss of generality, we can assume this f to be of this form, fz equals to lambda z. We can again take a conjugate of this f, which will fix the point infinity and 0, and that will be and that map will be of the form z goes to lambda z. So when we are conjugating the element, so we are also conjugating the group also. So and this theorem, it says that it is conjugate in PSL to R to a group generated by z goes to lambda z and z goes to minus 1 by z. So no harm has been done. Yeah, so safely we can assume this fz is equal to your lambda z. And so g, again, it fixes the point infinity. And if I assume g z is this Mobius transformation az plus b by cz plus d, so g of infinity is equal to infinity will imply that the c is equal to 0. So g of z is equal to a by dz plus b by d, and g is also not equal to identity. So now, if I take g of 0, suppose it is not equal to 0, so that will imply that this b is not equal to 0. And now if I take this commutator, so fg, f inverse g inverse of z, so this will be equal to z plus b by d times lambda minus 1. So this you can compute. And again, this b is not equal to 0. And this commutator, because fg, it belongs to your gamma. So this commutator, it belongs to your gamma. F and g both fixes infinity. So this commutator, it will fix the infinity. And by the structure, so b is not equal to 0. So this will be a parabolic isometry. So this will be a parabolic isometry, which is fixing the point infinity. And also we have this element f, which is a hyperbolic element which fixes the point infinity. And both these elements, it belongs to your gamma. Gamma is a quotient group. So we have a parabolic isometry and a hyperbolic isometry fixing the point infinity. So that cannot happen. So we have a contradiction. So this contradiction will prove that, so this b is equal to 0. So b is equal to 0. So therefore g of z, it will be of the form a by dz. So therefore fixed point of g is 0 and infinity. So therefore, so we have started with two elements. So fz I have taken to be of this form lambda z, and you can take g to be any arbitrary non-identity element. So we have proved that g of z is of this form a by dz. So therefore, so all the so hyperbolic isometries of this gamma, it is fixing this 0 and infinity. So fixed point of this gamma is 0 and infinity. So all the elements, it fixes 0 and infinity, so they will commute with each other. And by our previous result, so this gamma, it will be a cyclic group. So what we have proved that, so if all the elements of gamma are hyperbolic, so then gamma, it is a cyclic group. And now suppose if gamma contains all parabolic elements. So again, without loss of generality, so you can assume that, so gamma dot infinity is infinity. So therefore, fixed point of gamma, it's just infinity. So again, by our previous result, so this will prove that this gamma is cyclic. Okay, now let us move to the next case. So suppose there exists a point Z0 in the space upper half plane union union the boundary of this upper half plane, such that this orbit is consists of only 2 points. So let us take gamma dot Z0 is Z0, these 2 points Z0 and W0. So note that this Z0, it will automatically it will be contained in this gamma dot Z0 because gamma contains the identity element. So this orbit, it just contains only 2 points Z0 and W0, so that we have assumed. So now each element of gamma, so either interchanges the Z0 and W0 or fixes them. So again, we can take a conjugate of this group gamma such that, so this orbit, we can take it to be 0 and infinity. So therefore, without loss of generality, Z0 is equal to 0 and W0 is equal to your infinity. Okay, so the next observation is that, so this gamma, it cannot contain parabolic elements. If gamma, if it contains a parabolic element, so then, so that cannot, first of all, interchange the 0 and infinity. So then it will fix both infinity and 0, so that is not possible. So that's why this gamma, it cannot contain these parabolic elements. So the only possibility is this gamma can contain elliptic or hyperbolic elements. So if gamma contains only hyperbolic elements, so then fixed point set of this gamma is 0 and infinity. So then gamma is cyclic. So that already we have observed. And if gamma contains only elliptic elements, so then again gamma will be cyclic group by your previous result. And so one can show that this gamma is conjugate to this cyclic group generated by Z goes to minus 1 by Z. So yeah, so this can be done. And if gamma contains both hyperbolic and elliptic elements, so therefore, so this gamma is conjugate to the group generated by Z goes to lambda Z, and the map Z goes to minus 1 by Z. So for case 2, so this we are done. Now what is the case 3? So suppose some orbit of gamma has more than 2 points in upper half plane union the boundary. And it is, of course, it is finite. So orbit of a parabolic or hyperbolic element is either infinite or at most contain 2 points. So again note that, so we have assumed that orbit is finite. So we cannot take here this orbit to be infinite. So orbit by our assumption, the orbit has to be finite. So orbit of a parabolic or hyperbolic element is either infinite or at most contain 2 points. So therefore, this gamma, it cannot contain parabolic or hyperbolic elements. So this implies that gamma contains only elliptic elements. So this will imply that this gamma is cyclic. Okay. So now the next theorem, it says the following. So a non-elementary subgroup of PSL2R, it must contain a hyperbolic element. So what is the proof of this? So suppose gamma does not contain hyperbolic elements. So if all non-identity elements of gamma are elliptic, so then gamma, it becomes an elementary group. So that cannot be possible. So therefore, so there exists a parabolic element in gamma. So again, without loss of trinity, we can take a conjugate of this group such that there exists and so okay, so without loss of trinity, we can assume this thing that this map fz equals to z plus 1, it belongs to your gamma. And now let us take any element g z equals to az plus b by cz plus d belongs to gamma. And now you take this isometry up to the power n, compose G, take the trace of that thing, take the matrix corresponding to your f to the power n, compose G, take the trace and take the square of that thing, that will turn out to be the square of a plus d plus nc. So this gamma, it does not contain any hyperbolic element, and if n compose G, it belongs to your gamma. So gamma contains only elliptic and parabolic elements. So therefore, so this left hand side, this has to be less than equals to 2. Trace of this matrix, this will be less than equals to 2, and square of that thing will be less than equals to 4. So therefore, what we have, 0 is less than equals to square of a plus d and c less than equals to 4. And this is true for all n. So this can be only possible when c is equal to 0. Meaning, so g of infinity is equal to infinity. So therefore, so this infinity is fixed by all elements of gamma. And again, so this will prove that this gamma is elementary because the orbit of infinity will be just a singleton set infinity. So this is a contradiction. So this is a contradiction. So the contradiction is due to this assumption that gamma does not contain any hyperbolic elements. So therefore, a non-elementary subgroup of PSL2R, it must contain a hyperbolic element. Okay, so I'll stop here.